Hey, physical science students, it's Mr. Olive on behalf of Mr. Marquis and Mr. Flugum. Last lesson of the school year. So after you're done with this, if you've been doing all the distance learning stuff, you're done. So it's kind of cool. All right, just to kind of review some of the different types of waves that were talked about by Mr. Marquis and Mr. Flugum. The compressional waves, the examples I'm going to give you here of compressional waves are how bats or sperm whale use echolocation to detect prey and eventually to track down and catch prey. Through two different medium, bats use it through the air and a sperm whale uses it through the spermaceti oil in its head and then also through the water. So echolocation are compressional waves, just smack, 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 smack as it travels through the air. Transverse waves, those were the classic ones talked about where you have the trough, you have the crest, you measure the amplitude, you've got the resting position, all those vocabulary terms and just what we think of when we think of waves in the water, transverse waves, up and down, up and down. We're going to focus mostly on earthquakes for this unit and how that pertains to a wave unit. So the whole unit's really going to be about earthquakes. So the chief cause of earthquakes, the main thing that causes earthquakes are just plate relationships. If you think of our Earth's crust as a jigsaw puzzle that's anywhere from a few kilometers to 40, 50 kilometers thick, depending on where it's at, where these two plates come together, depending on how they come together, the likelihood is high that it could cause earthquakes. This area highlighted on the map here is what's called the Ring of Fire. And there's places where plates are colliding and causing mountain ranges to come straight up. There's places where they're diverging, and there's places where they're kind of rubbing together side by side. So all throughout the Ring of Fire, you're going to see volcanoes and earthquakes, a lot of tectonic activity. One of the more famous plate relationships is down in California, and the reason it's more famous is because that's where Hollywood is located. It doesn't necessarily have anything to do with the amount of danger, but there's a lot of population down there, and so this San Andreas Fault that goes right up through LA and on the way up to San Francisco are just two plates rubbing next to each other, kind of like that, side by side like that. If you were to look at it from the air, that's what's called a transverse or strike slip fault line, and it does release energy. You know, you get 4-point earthquakes in LA, which can cause some destruction. We live on a subduction zone. So a subduction zone, here's Oregon or Washington in Canada, but we're under it too, is where a plate, and in this case it's a plate called the Plate of Juan de Fuca. It's an oceanic plate. It's in the ocean, it's thin, and it's getting forced down under the North American plate, which is heading towards it. And it goes, it's at about the speed that your fingernails grow. One gets forced down under the other one. This is something that causes earthquakes. It caused a big one. One of the oceanic subduction zones caused a big one a few years ago that really thrashed Japan. Our whole geology and geography, everything depends on our relationship with the plate off of the ocean's crust. So if you look here on the left, you'll see the Cascade Range, which is kind of a crumple zone. It's right where we meet the plate and causes a smoosh up. There's no volcanoes in the coastal range. It's just from that Juan de Fuca smashing into the North American plate that causes that mountain range. And then as it gets forced under and comes back up, all that lava causes our Cascade Range. So our Cascade Range is much bigger peaks than the coastal range, but caused by the same plate relationship. In the case of an earthquake, where two plates meet, that's called a fault line. And when they slide or slip, that's going to cause an earthquake. And down below ground, it's the focus is where that slip happens. So that's the cause of the earthquake, is called the focus. It might be 7 miles deep. And then the epicenter is up on the surface where you experience those waves directly above the focus. So the epicenter may be miles and miles away from a fault line, but down below it, directly below it, that's where two plates are experiencing a slip. Yeah. Now, when you get an earthquake, and this is where we start talking about waves a little bit, when you get an earthquake, we're just going to focus on the two main types of waves that occur. Um, on this diagram here, you have red. Okay, and if you just focus on the red arrows, these are the first waves that you're going to experience when an earthquake takes place. They're what's called P waves or primary waves. And those are interesting because they can pass through all layers of the earth. The earth's got a crust, which is mostly a solid, and then below it, it's got a mantle, which is sort of like a super hot toothpastey stuff. And then below that, it's got the inner core, which is super hot, almost as hot as the sun, but liquid metal. And P waves can go right through that liquid metal and even pass through the most dense part, just a super tightly packed metal core, iron core. And P waves can pass right through that. So if you have an earthquake, say in Oregon, it can be felt clear on the other side of the world in India. So the P waves are what can pass through the earth. Now, we started learning about this inner core and this outer core because of S waves. S waves can't make it through the earth. They get deflected and pushed away. So you don't feel it directly on the other side of the planet. You feel it off to the side. And S waves are represented here in blue. And they're secondary waves that come afterwards. And they're a different type of wave too. We'll talk about that. Okay, so the biggest difference between P waves and S waves. P waves are compression waves. Okay, so kind of like the way a bat talks through echolocation, that's the way P waves travel through the Earth's crust. So it's sort of a smack, 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 and that's the first waves that you would feel in an earthquake. S waves are transverse waves. So the difference, though, instead of going up and down like a water wave might, they more move the way a shark moves through the water. They go side to side, or like a snake moves on the earth. They go side to side, and they're still a transverse wave, but they go side to side, and they hit pretty hard. Yeah. So P waves, like I said, can be detected clear on the other side of the world because they're compressional waves, and S waves get veered off. They get the outer core kind of pushes them off to the side, and you can't feel those on the other side of the world. They can be felt somewhere else. Okay, we detect these waves using something called a seismograph. Now, interesting thing about a seismograph, there's one at the University of Washington, and they were detecting all these earthquakes that were measuring 2.0 on the Richter scale, and they come to find out that it was a year that Seattle Seahawks were playing really good football, and they were en route towards playing in the Super Bowl, and the crowd just was super energized, and you could literally feel a 2-point earthquake, um, S waves, just right over there at University of Washington, which is across Seattle from where the Seahawks play. You could literally feel it on a seismograph. But down below, you'll see I pulled up an image on how you could make a homemade seismograph. But seismographs, basically, they detect movement of the Earth's crust. Okay? And we measure those earthquakes using something called the Richter scale. Now, the Richter scale, as it says right here, each level indicates 10 times the amount of shaking, 33 times the amount of energy. So when somebody says, I lived through a 4.0 earthquake, and another guy says, yeah, well, I lived through a 5.0 earthquake. That's 10 times more powerful than a 4.0 earthquake. So quite a bit difference in terms of energy. So the Richter scale is how we measure these earthquakes. Anything that exceeds an 8-point earthquake is going to be cataclysmic, enough energy to take out the city of Portland. So 8.0 earthquakes are tremendously huge. In my lifetime, there's been one to exceed 8.0, and that was down in Chile, and it was devastating. Here you see some, oops, let me go back. I'm going the wrong way. There we go. Here you see some evidence of those compression waves. The best evidence that we can hope to find is things that we've built that are supposed to be in a straight line, man-made structures that are perfect straight lines. And then when an earthquake hits, those things get separated. So you can see that P waves hit this area and it moved the fence so that it's no longer lined up. And this is S waves on railroad tracks. So railroad tracks sometimes provide really good evidence of earthquake, and hopefully you catch it before a train's going down the tracks. But you can see that earthquake hit this train track and really altered its course. Okay. Okay, some questions about earthquakes and how they pertain to a wave unit. So first of all, we've got about 5-6 questions to answer. Let's start with what's your name and what period do you have physical science, so that when you share that with Mr. Flugum, Mr. Marquis, or I, it's easy for us to grade. Helps anyway. Okay, so this first question, for centuries, Japan has developed architecture designed to withstand major earthquakes. Why would earthquake-resistant building methods be such an important part of Japanese culture? And try to use a map to explain. So look at a map and kind of explain why. So why would that be a big part of Japanese culture for centuries? They were making homes out of essentially paper products so that when roofs came crashing down, it wasn't lethal. Not putting big wooden heavy beams. Right. Next two questions have to do with this this graph right here. So first question number 3, what device made this chart? Might have to go back and look at some of the slideshow. What device made this chart? That's question number 3. And then question number 4, same chart. So here's the question. How much time passes between the P waves and the S waves according to this graph? So if you look at this chart, how much time takes place between when a particular location gets hit by P waves and then by S waves? Okay. Hopefully, before you watch this slideshow, you watched a video that talks a little bit about Oregon and the potential for an earthquake. I'm ask that you do that, and hopefully you do that. Okay. This next question, why do geologists believe that Pacific Northwest is due for a major earthquake? Question number 5, what's going on that makes people, scientists, geologists believe that we're due for a whopper? Okay. What is the name of the scale scientists use to measure earthquake strength? And then the last question, how much stronger is a 5.4 earthquake than a 4.4 earthquake in terms of shaking, strength, energy released? Remember that waves just move energy through a medium, and in this case it's going to be all the different layers of Earth. Here's the first question. Here's the second question. Here's your third question. Most of this is going to be based on a video that you watch, hopefully, before the lesson. Last question. And for those of you that did all of our lessons, Mr. Marquis, Mr. Flugum, and I, we thank you. We appreciated being able to still try to teach you guys a little bit. And at the meantime, those of you that bought into this and worked hard, hopefully you learned some stuff as you finished up physical science. You guys have a great summer, and somehow, some way, we're going to see each other in the fall, hopefully a lot. because we're ready to teach some students. We all are. So thank you guys. Have a good summer.